What is mode shape? Actually, mode shape is a specific pattern, a fixed bending pattern, in which a system prefers to vibrate when left on its own with no damping and external forcing. Suppose if you have a cantilever beam, something like this, for example, this is our cantilever beam, and it's going to distort from its initial position, and if we set it in motion, it may vibrate like this. This is going to be the first mode shape. And second mode shape could be like this. In that second mode shape, there is one point that's not going to move left or up or down. That's called node. If it is third mode, it will have two nodes like this. Here one node and here one node. Like that will have two nodes. Nodes means that's not going to move up and down. If higher frequencies, it will have more curves. Okay, so it is independent of time. So it's going to be the fixed pattern. Always the first mode it will be deflect like this, second mode will be like this, and third mode will be like this. Fourth mode, higher modes, it will be different curvy patterns it will be coming. It only describes the relative motion between different parts. So what is it doing? It's doing only the relative motion of the points. For example, if this point is here, we will take one example. Let's take one example. Suppose if I have my cantilever like this, and I have two nodes, here one node and here one point, I can say a point. So this point also it will go down, this point also it will go down. That means both points are coming down, so it will deflect like this. So this is the first point and this second point, it will look like this. Okay, this is the first mode. Second mode, what would happen? Second mode could be this point is coming down, this point is going up. So it will go like this and it will come like this. So this point is going here and this point is going here. So first mode, both are coming same direction, 1 say, and 1 or 0.3, because it's going to be 0.3 or 0.4, like that one it will come, because the displacement at this edge is more and here it's less. So we will take 1.3, but next one it will be here 1 and that will be minus 0.3. So next mode shape will be, we can say next mode shape, second mode shape will be 1 and minus 0.3, like that we can say it. So this is showing the relative motion between different parts. It's a special pattern, it like a shape of vibration, like a shape of vibration. For example, in a ruler clamped at one end and flicked, and the first mode looks like a smooth bend. That's what I was telling. And the second mode might look like S curve. It looks like a S curve. And third mode, higher modes get more wavy and complex. Each structure, beam, rope, bridge has its own set of modes determined by its physical properties, mass and stiffness, and boundary conditions. So it depends only on the mass and stiffness and boundary conditions. It does not depend on gravity or acceleration. So wherever it goes, the natural frequency will be the same, whether it's in Earth or Moon or Mars. Wherever it goes, the natural frequency and mode shape will be the same thing. Next one is modal shape. Let's understand what is modal shape. Let's understand what is modal shape. Modal coordinate. Mode shape we have seen. Modal coordinate. Modal coordinate is usually denoted QI of t, tells how much of ith mode is active at a particular time. So I have told you, for example, when we have a 2 degrees of freedom, it has two modes. So modal coordinate will tell at particular time of time which mode is active. So if the modal coordinate for first mode is active, means that modal coordinate value will be higher. Modal coordinates are functions of time. So first mode and second mode, like it depends on the time, it varies, and they will tell how strong or excited each mode is. And if you have 10 modes, maybe some particular modal point is more, means that particular mode is going to be active, that structure is vibrating at that particular mode. Each mode has corresponding modal coordinate. Each mode has corresponding modal coordinate. Think of mode shape as directions and in a special shape, and modal coordinates as how far it's traveled along each direction at that moment in each time. So you can say that first mode is like this, second mode is like this, and third mode we can say it's in different direction like this, and fourth mode we can say that it is somewhere here like this direction. So we can say in the out of this the third mode has higher magnitude. That means modal coordinate for this mode is more. That means when it's vibrating, that point will vibrate in this direction more, other directions are almost equal. So actually its vibration is a combination of all the modes. It can vibrate in a very different way. Okay, but this different way, like a complex way, if we split into each model shape, we can say that first it will bend like this only. Second shape, it will bend this curve shape. Third one, it will have something wavy shape. And fourth one, it will be furthermore. So what we are doing, if we combining all these things, that would be the final motion. So in model analysis, we are making the complex vibrations breaking down into number of mode shapes, and we are finding out which mode shape is highly active, highly participative. Based on that mode shape, the model coordinate will be more. So model coordinate, it will show how much that mode is active. Okay, so yeah, let's say system has n degrees of freedom. The actual displacement at time t, we can say Cartesian code x of t. This is the Cartesian coordinate, and this is the mode shape. This is the model coordinate. X is the vector of displacement at each point that we have seen, like cantilever and is moving more, so that displacement is more, and near to the fixed end the displacement is less. So at each point what's the displacement, that we can say in terms of Cartesian coordinate. And model matrix mode shapes, we know model coordinates, that shows like how amplitudes of each mode over time, how each mode is behaving, like that we can say. Mode shape tell us how the system deforms. Mode shape will tell that it's a fixed shapes. This is the first mode, this is the second mode, like that. These model shapes are fixed shape, but model coordinate tell that how much of that shape is involved in that motion. Okay, you can imagine like in some music, like each key has a fixed sound and volume you play it, that model coordinate, how loud is that moment at that moment. The final sound, real motion of system is a mix of all keys played being passed at the different volumes. We can have some one example. For example, 4 degrees of freedom of cantilever rod. Let's say cantilever rod clamped at one end, it's a model with 4 points. It has four mode shapes. Definitely 4 points means 4 degrees of freedom, four mode shapes. First mode shape is 0 0.1, 0 0.5, 0.81, and second mode shape is minus 0.2, minus 0.1, 0.61, 0.2. At any time, the displacement of all 4 points can be described as x of t is q1 of t into phi1 q2 of t into phi2, like that will come. This means the total motion is a superposition of four spatial patterns, each scaled by its own model coordinate. So mode shape is a pattern of motion across system. How it shows how each point moves related to each other. It does not depend on time, but modal coordinatum is the amplitude of that mode at that particular point of time, that depends on time. And Cartesian coordinates also, it varies with respect to time, because when you are vibrating something this kind of uh, raw, it will vibrate like this. At one point of time it will be more, and after that it will be less, after that it will be in reverse direction, it will be coming more. So it will vibrate, and this first second it may go here, and 0.2 second it may come down, 0.3 second it will come down, it will go up. So it varies with time. That's why the Cartesian coordinates varies with time. For example, at x equals 0, what's the displacement in this y direction? X equal to 5, what is the displacement in the y direction? Y x equal to, what is the displacement in up and down direction? So that's the Cartesian coordinate. Okay. Relationship between Cartesian coordinate and the model coordinate is we are multiplying with more shapes. So let's discuss. Look, when I flick this rod, it bends in a certain way. That's right. But it's not just random. It's kind of dances in patterns. What do you mean by patterns? Great observation, Lily. When the rod vibrates, it moves in a specific mode shapes, fixed patterns showing how each point moves related to others. So like a choreography for the rod. Exactly. So each mode shape is like a dance step. I see the rod move differently at every time I flick it. How? Because the actual motion is mix of these dance steps. Each step's intensity changes over time, that intensity is called a modal coordinate. So the mode shape is a pattern and modal coordinate is how strongly that pattern show up. So mode shape is a pattern and modal coordinate is how strong that pattern show up. If that coordinate is high, that pattern shows up more. If that mode shape modal coordinate is less, that mode is not that much active. It does not show up. So you can think of mode shapes as a fixed poses. You are giving the poses. And modal coordinates shows how big or small that the rod stretches into these poses at each moment. So if the rod has 4 points we watch, that's 4 degrees of freedom. We can describe the total movement by adding all 4 mode shapes, each multiply its own modal coordinate. 4 mode shapes, each multiply its own modal coordinate. So x of t, we can tell modal coordinate multiplied by mode shapes. That's the thing. Like x of t is the displacement at all points, y is the mode shapes, and q of t is modal coordinates time dependent. Mode shapes are fixed patterns. So if I know all the qi of t, I can predict exactly how the rod moves at any time. So if I only excite one mode, only one modal coordinate is big and the rod vibrates mostly in that mode shape. Yes, if you are vibrating, if you are trying to excite one particular mode, that particular mode's modal coordinate will be big and then rod vibrates that mode mostly in that one mode. You got it, Max. That's how engineers simplify complex vibrations. But can modal coordinates be zero? Yes, if a modal coordinate is zero, that means that that mode shape does not contribute to the motion at that point of time. So at that point of time, that motive is not contributing. So can modal coordinates be more than one? Yes, of course. They can be any real number, the positive or negative, representing how strongly and which direction the mode is active. So it's like the rod is performing a dance choreographed by many steps, and modal coordinates tell how loud each step is played. Beautifully said. Magic of mode analysis. Hey, watch this. When I flick the rod, it bends and sails like it's dancing. The points don't the points don't all move the same way. Some move a lot and some hardly at all. Why do some points move differently? Isn't the one rod each excellent question? The rod's vibration is made up of special shapes called mode shapes. Each mode shape shows a unique pattern of movement across the rod points. Like different dance moves for the rod. Exactly. Imagine the rod is performing different dances. Each dance is a mode shape, and that final spatial pattern that does not change over time. When I flick the rod, it looks like a mixture of dances. Sometimes the middle moves more, sometimes the end swings. That's where the modal coordinates come in. They tell us how much the rod performs each dance at any moment. The modal coordinates are like volume knob for our each mode shape. So the rod's total movement is just a mix of all the mode shapes, each with its own modal coordinate. Yes, mathematically, if the rod has 4 points, the total displacement at the points, we can get it like this. So these mode shapes are fixed vectors describing where to move. Yeah, mode shapes are fixed vectors where to move, and modal coordinates are numbers that change with respect to time, tell us how much to move, where to move, and how much to move. It's in this direction, but how much? Too high or too less? And if you know the mode shapes and modal coordinates, you can rebuild the entire motion. Can the modal coordinates be zero? Yes. If a modal coordinate is zero, the mode shape does not affect the motion at all time. At that time, the can modal coordinates be bigger than one? Yes. It can be any real number. That contributes a lot if it's more. So how do we find the modal coordinate? Modal coordinate. If we see the rod moving, given the mode shape matrix, you can multiply the inverse of phi and displacement vector, you can get the modal coordinates. This transformation changes Cartesian coordinates, real point displacement to modal coordinates, mode intensities. Modal coordinates are nothing but the mode intensity, how intense that particular mode shape. So modal coordinates and Cartesian coordinates are entirely two different things. Cartesian coordinates is real point displacements, but there is a relation between the Cartesian coordinate and modal coordinates through mode shapes. So modal coordinate says that how intense that particular mode is going to be. But mode shape is a fixed menu pattern. Okay. The Cartesian coordinates tell us how each point moves. The modal coordinates tell us how much each mode shape is active. So there are two different things. In the rod, for example, if I have this kind of rod, my Cartesian coordinate will tell, and if I have some points like this, my Cartesian coordinate will tell how much this point is moving. But my modal coordinate will tell how much each mode shape is active. That model coordinate depends on the mode shape. Cartesian coordinates, that depends on the position. Okay. Now using the known mode shapes, and you can find the model coordinates at any given point of time by solving. That means even though the rod moves in a complex way, model coordinates break down into simpler motions. So model coordinates, with that we can find out which motion is going to be very much active. So even if it vibrates complexly, we can break down into the simpler motions. It's a powerful way to analyze vibrations, especially in big systems like bridges and things. Use this know Use this to know which modes to watch out for, like dangerous resonance. If one model coordinate grows very large, it means that mode shape is going to be vibrating strongly, possibly dangerously. So model coordinate tell us how much the rod is dancing at a particular mode. Mode shapes tell us which way it dances, whether it's a S type or a wavy type. But he is dancing so much in that S wave, or how much, that's dependent by model coordinate, and how is by mode shape, and how much is by model coordinate. Understanding these lessons help engineers, business savers, as I said. Set up system one, like you have a 4 degrees of freedom, like this x, the displacement vector x, this vector source mode shape matrix, we know 5 1 5 2 5 3. This is a mode shape matrix. Each column is a mode shape. Model coordinates vector is this one, q of t equal q1 t q t, and tells us how much mode shape q1 I of t tells how much mode shape is active at that point of time. Relationship between displacement model coordinates. Yeah, this is the point.